I see a significant difference. It's something you hear maybe a bit more often than statistics would really call it significant. Let's discuss about that significant thing. Hello, I'm Tom. Welcome to my channel where we make operational excellence practical. Today it's really a bit of a direct lesson, right? This is just a piece of statistics, a little bit of a tool, because we use it a lot, especially in Six Sigma, but in basically all kinds of comparisons and reporting. The concept of what is a significant difference, or do we really see a difference, it comes up quite a lot. And it's just good to know what we're actually testing, and that's why we have this explainer of significant difference as it is being used, for instance, in a t-test or in an ANOVA type of testing. So what we have there, and we'll take the t-test as an example, is that we want to know we have measured sort of the same thing but in two different ways. So for instance, before or after our project, we measure how long it takes to heat up a kettle. Or we have a gas burner and an electric burner. Is there a difference? Or we have two identical burners, we think, for our process. How long does it take either of them to warm up our process? So when we want to know, is there a difference or not? It doesn't really matter, do we want there to be a difference, right? In the case of the two identical burners, well, two similar production lines, similar burners, we want them to do the same, to the process, to the product. In the case of we did a project on the burner and now we think it's more efficient, we sort of want the new situation to be quicker, right? So we want there to be that efficiency. Both we test with formally hypothesis testing. So we test, well, we take samples. What's the chance that basically they come from the same system? In statistics terms, from the same population. And if that chance is less than, usually we say less than 5%, so P, probability, is smaller than 0.05, then it's significant. Right, but this P value, what does it mean? When we have two systems, right? So how long does it take our heater to heat something, to get it to the correct temperature? Right, so this is our time. And we have a purple and a green set of data. And what is that? The purple set, that is our new stuff, right? So after our project, we measure a couple of times how long does it take our production line to fully heat up the system, the vat. And we checked this 5 times and we measured a couple of time values. Now, we did the same before we even started the project, and the green one, we also made 5 measurements. And what does statistics do? It says this is a sample, right? We don't know the truth, like a divine truth behind it, we don't know. We can only measure. And we measured it 5 times based on sort of assumptions around heating times and heating curves. We say it's probably a normal distribution behind it, probably. So, but is there a difference between this green and this purple? Let's check the mean values, right? Because if there's a difference in the mean, there must be a difference in the actual result. So it's about here. And for the old situation, it was about here, right? So there's a couple close to there, there's one dragging it down. Those means, that's quite a difference. So yeah, great. Great work, team. You made a nice, well, it's a positive effect due to the negative difference in heating time, right? You made the process quicker, better. Great. Now, what does statistics say? It says, well, wait a minute. There's actually this one value you measured that was even more than the average in the old system. And there's a couple of old systems. There is some mixing there. Let's take a closer look. And in the background, what sort of happens when you do something like a t-test, or when you do something like ANOVA, analysis of variation, of variance, and even all kinds of things like f-tests, what it does is it sort of extrapolates to the entire population from this sample, right? So it says, well, if we have these 5 measurement points, yeah, we have a nice mean, but we assume that there is a certain distribution underneath. And if we do the same for the green ones, well, we see this mean, but, and based on this, a statistical test, a t-test, will say, no, there is no significant difference, because, and here's where sort of the what is the test doing in the background comes along. If you know this normal distribution thing, and you say, well, our new system has decreased the time, so we're gonna put a significance level there. As I said, you don't need to choose 5%, but this is a very common level in all kinds of basic industrial applications. Some people choose 10%, P is less than 0.10, but usually you get 0.05, right? So do we have that here? What does it mean to begin with? In this normal distribution, we can say, well, so many standard deviations, that's 64%, that's 90%, that's 99%. We can also do the 5% one, and the 5% one, that is at about, what is it, 2.1 standard deviations. But if you do an inverse normal distribution in Excel, you will see that it's somewhere here. There is this, okay, we have 5% of our distribution. And then what does the tests do? It says, okay, this mean, is it in the 5% or in the 95%? And if it is on that side, that is significant. But if it falls on that side, so if it's not at least 95% sure that this really is a different population, it says nah. So purely based on how I draw it here, 5%, maybe yes, maybe no, 10% it'll probably make. But this is what a t-test does. Now, let's check a sort of similar situation, but with different results. Say that we do the same, and here we did our measurements. These measurements, they're very different. Right? The old situation has an average here, and the new situation has an average here. Same difference. But these samples, they are way closer together. So if we estimate the distributions underneath them, if we estimate this bell curve, they will be very narrow. These, they don't overlap. The mean of this new improved situation, the shorter time, it doesn't get anywhere near the 5%, not even the 1%, not even the 0.1% of the other distribution. So what does our statistical modeling say? Well, this here, not really significant. This, yeah, this is significant, right? And that is what the test does under the hood. So when you do a t-test, it does a whole bunch of things on the background. One of those things is if you only have 5 samples, you can't really just use normal distributions. Don't worry too much, because a t-test uses a student distribution that takes into account that few samples, they need to make some corrections. All done for you. This whole calculation of how far should they be apart, that's in the t-value and in the significant t-value. A whole bunch of things happening under the hood. In the end, you just get this number, a p-value. if the p-value here, it will be something like 0.07, not significant. Here it will be something like 1,000th or so, or a 10,000th, so super significant. That is the value you get back, and this picture is what it sort of does under the hood. Now, why do we use this? Because we don't just want to say, hey, there is a difference. Right? Our general assumption, in statistics, our null hypothesis, should be, no, it's the same, right? If we can't really see a difference, we call it the same. Now, you might say, hey, there's a more than 50% chance that it's different. Statistics is quite a bit more strict. Of course, you could put your p-value limit at 0.5, so 50%. Nobody in sort of physical sciences does this. 0.10 happens, but 0.05 is very normal. Chemists tend to go further, 0.01. So yes, there's reasons why you want to change this, but if you're doing Six Sigma work, just use 5%. Right? It's strong enough, but it's also not overly strong. And that's what it is testing. This is very important because we tend to use just a couple of samples. And if you have a large variation in your system, so if your heating times, they're sort of, all over the place is so negative, but sometimes they're 30 minutes, then they're 35 minutes. That just happens. There's easily 5% spread. Then when the new system makes it 1 minute faster, is this really a difference, or did you just get a couple of lucky samples? The other way to go around this is to make a very large sampling, and then the statistical test will also help you, because if you do have these underlying, but you take 20 samples, it will tell you, oh, this actually, it is significant. Because what we did when we said it's not significant is we said, nah, all of these, they sort of come from this distribution. All right? That's the hypothesis 0. The null hypothesis is it's the same. That means that when you want to prove that you really had an effect, which is sometimes nice, sometimes not, then you basically say, unless I really see it, I'm going to say, nah, there was no effect. Let's just ascribe this to chance. If you still are convinced that there actually was an effect, go take more samples. But also know that quite often the statistics are sort of right. If you have a big variation, you probably have some measurements that just happen to be smaller. And one of the main things that I want to add to this explanation is don't go p-hacking, as it's called. So if you investigate one of your processes and you're just going to say, well, what could be the cause or the effect or a change, and you just take 20 factors and compare last year to this year, there is a big chance that in those 20 factors, one of them will randomly, sort of, show you a significant difference. Because 5% is 1 in 20, so purely by chance, 1 in 20 will give you a random significant difference. What you do is you put a thesis there, a hypothesis, you say, I know that the time should be shorter, right? That was what we worked at. Now let's check. Or you say, my operators are telling me that breakdowns this year are really more on that line than last year. Let's go and check the data, but not. Let's check breakdowns, setup times, cleaning times, heating times, speed losses, and let's see if there's anything different. Because then even the 5% won't help you. This is a rule that you use if you already have a good idea what you think happens. You just use it to support or not support that hypothesis. Now, I hope that this helps. There's a whole bunch of things to explore here, but we're not going to go into all of the statistics. If there are some other statistical concepts that are quite well used within Six Sigma that sort of elude you, let me know in the comments, because I do like explaining these things, and I hope it will help you as well. For now, just hit that like button, subscribe to the channel if you want more of this, and I wish you the best of luck using these sort of light statistics in improving your business. As always, don't forget to also enjoy the operational excellence journey.